Okay, today we're going to go over common series equations that can be represented as Taylor and Maclaurin polynomials. So I should give a quick preview. Taylor and Maclaurin polynomials are infinite series, and they're a way to express functions. I'll go over at a later date how to create and derive these functions. However, in the meantime, we're just going to go over some common terms that can be represented by them. And these will appear very often on AP exams and whatnot. Okay, so the first two we're going to look at are cosine x and sine x. However, before we get into that, let's take a look at these infinite series themselves. So, as I said earlier, we'll go over Maclaurin-Taylor polynomial series later. However, you should know that these are ways to express functions in a way. And by filling in the two here with something else, you can fill in the two here. Or for instance, if you add x squared in place of x, then you would, of course, replace it within the Maclaurin polynomial as well. So they're very useful ways to estimate functions, and they go on forever, essentially. Now, these polynomials are commonly written with 4 first terms, and then a plus, dot, 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 plus, because it's infinite, and then another term, which is the general term for the sequence, as you'll see. If you were to replace n with 0, you'll end up with 1 over here. If you were to replace n with 1, you'd end up with negative x squared over 2 factorial. So those are just ways, or that's just a little background info on Taylor and Maclaurin polynomials. They're really quite fun, very important, and pretty easy to memorize how to derive one. However, let's go over cosine x and sine x. Cosine x can be represented by 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power of 6 over 6 factorial plus dot, 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 plus negative 1 to the power of n plus 1 times x to the power of 2n over 2n factorial plus dot, dot, dot. So since this is an infinite series, although it can be used to evaluate the value of a function or whatnot, it's never going to be entirely accurate because you'll never be able to plug in every single value of x into every single term of this sequence because it's infinite. So you'll commonly have to shorten it. For instance, you could say, what's cosine 2 to the 6th term, or sorry, the 6th degree? And that means that you'd replace every instance of 2 up to you'd replace every instance of x with 2 up to the term with a degree of 6ths. Meaning everything after here you disregard and you only look at these first four values. So that's just a little more background info. Now, these common Taylor polynomials and Maclaurin polynomials are, there is a pattern, although they are a bit difficult to memorize. However, as I said earlier, you can derive your own. So if you forget, you can just find it again. Now, sine x can be represented by x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial plus dot, 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 plus negative 1 to the power of n plus 1 times x to the power of 2n plus 1 over 2n plus 1 factorial plus dot, dot, dot. Okay, there are just 3 more that I'm going to go over. E to the power of x can be represented by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 plus x to the power of n over n factorial plus dot, dot, dot. All right, so 1 over 1 minus x can be represented by 1 plus x squared plus x cubed plus dot, 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 plus x to the power of n plus dot, dot, dot. And finally, natural log 1 plus x, which is a rather new term that you'd see represented by infinite series, at least on the AP exam. They've introduced this and it's become more common, but nonetheless, it's pretty easy to memorize. X minus x squared over 2 plus x cubed over 3 minus x to the power of 4 over 4 plus dot, 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 plus negative 1 to the power of n plus 1 times x to the power of n over n plus dot, dot, dot. Okay, so this is practice problem 1. We're told that there is a function f of x that can be represented by e to the power of x minus 1 over 1 minus x, centered at 0. Find f of x to the third degree. Now, this centered at 0 part may seem unfamiliar to you, so just disregard it. Like I said, I'll make a video on it in the future. And this problem itself may seem a bit complicated. You may not know what to do, but that's fine. So let's look at the first term of the function e to the power of x. We can represent e to the power of x, as I showed you earlier with the Taylor / Maclaurin polynomial, but we're only going to write it out to the third degree. So let's start off with 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And of course, you can probably already see the pattern if you haven't yet memorized it, but it goes on for a while. That doesn't matter, though. We're just going to focus on the first 4 terms because this is the only term with a degree of 3. Next, we'll look at 1 minus 1 over x. Again, we're only going to go to the third degree. And this can be represented by 1 plus x squared plus x to the power of 3. And again, as you can imagine, it's infinite, so it'll continue onwards. Okay, now we just have to write these out. We can say that f of x is equal to these first 4 terms, and I'll use these as an approximation to substitute in for e of x. Minus these terms over here. So minus 1 minus x squared minus x to the power of 3. Now, typically with questions like these, you can see that mine doesn't quite make sense. Why would we substitute these 2 terms in for less accurate versions? And that's because you'll commonly be told to find like x to the power of 5 or something, but it's too complicated at the time. Or at the time of me teaching this, so just ignore that. Okay, now we end up with this approximation for our function f of x. I should state that this is actually approximately equal to this. Now I can start crossing out terms. 1 minus 1 is 0. X minus x is, of course, 0. And now we end up with x squared, 2 factorial, plus x to the cubed 3 factorial minus x squared minus x cubed. And that's a rough approximation of our function f of x. And of course, if we were to you know what, in fact, let's do that right now. Let's find f of 1. Sorry for just throwing this in here now. Okay, we can substitute every instance of x with 1. So we end up with 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, minus 1 minus 1. We can simplify this further. 1/2 plus 1 over 6 is going to be equal to 2/3 minus 2. And that is good for now. Okay, so this is the final practice problem. It may seem unfamiliar to you, but it really is not that difficult. Now, if you'll remember if you'll recall from the formulas I gave you earlier for the infinite series, this general term may seem familiar. In fact, it's actually pretty similar to cosine of x, which I'll write right here. I'll just write the general formula, which is -1 to the power of n plus 1. Actually, let me make this a bit more formal. Okay, so the general term is -1 to the power of n plus 1 times x to the power of 2n over 2n factorial. And of course, this may look similar to the general term above, except that this x is actually replaced with a 3, meaning that this over here, this function cosine of x, is actually cosine of 3. And that is the answer to our infinite series up above.